I'm standing in front of a rock face that has many fractures in it. Fractures dominate subsurface behavior because they act as the superhighways of flow, and we need to be able to predict and optimize these systems. We've developed the software tool dfnWorks to be able to predict fracture flow in fractured systems that are often thousands of feet below the Earth's surface. What flows in these fractures is often water, gases, as well as hydrocarbon, and this makes it a very complex system because how all these fractures hook up and form a network and flow requires very complex modeling tools that we have developed with dfnWorks. Why is this important? Because the subsurface currently provides over 85% of the world's energy, over 50% of US drinking water, is critical for nuclear non-proliferation, and finally to be able to dispose of things such as greenhouse gases using techniques such as carbon sequestration. Hydraulic fracturing is transforming the way we extract oil and gas out of the ground. But right now, 95% of the hydrocarbon stays in the ground. It's very inefficient. We want to be able to predict where the fractures go and the fracture flow to reduce the environmental impacts and increase extraction efficiency. If we're talking about disposing of things in the subsurface, whether it's carbon dioxide or nuclear waste, we want to make sure that these don't just leak back out through fractures. So again, we need to understand how flow and fractures go, and that's what our tool does. So what do all of these applications have in common? Fractures.
Part of Los Alamos National Laboratory's core mission is a global security, and in particular, nuclear non-proliferation. dfnWorks' unique capabilities to run on advanced supercomputers allow us to predict gas migration in underground nuclear weapon tests performed by other nation states. This simulation shows how fractures created by an explosion connect to natural fractures of a rock and allow for transport of gas particles to reach the surface. dfnWorks has built-in tools to quantify uncertainties associated with model outputs, such as arrival time of gas particles, which is critical to determine when to send a plane to maximize chances of nuclear test detection.
dfnWorks simulates flow and transport through subsurface systems, in particular fractures in the subsurface. Flow and transport is simulated through interconnected networks of disks that represent fractures. A high-resolution computational mesh honoring intersections allows for accurate multi-physics to be simulated. Here, we're examining a hydraulic fracturing well site. The well is shown in blue, the fractures are in red, and the background fractures are shown in yellow. Depending on the requirements of the data, dfnWorks can be run from laptops to exascale computing. Here, methane gas being extracted from the system, represented as green particles, allows us to start looking at energy extraction efficiency and mitigation of environmental impacts associated with hydraulic fracturing. dfnWorks is setting a new standard for discrete fracture network simulations worldwide.
We're using dfnWorks for multiple applications. We work with Chevron and Apache to develop greener hydraulic fracturing techniques. SKB in Sweden, we are looking at techniques to dispose of nuclear waste. And for carbon sequestration and nuclear non-proliferation, we have large programs with the Department of Energy.